evening, everybody. Tonight we will be discussing the preliminary design for Tito's left hand. My name is William Cortez. I'm a mechatronics engineering student, and I'm the project manager for this group.
My name is Pete Matalich. I'm a mechatronics engineering student as well, and I'm going to be handling hardware design.
Brett Smith, also doing mechatronics, and I'll be in charge of software.
Douglas Smith, mechanical engineering student, and I'll be focusing on mechanical design.
Our industry sponsor for this project is Charlie Roberts. Charlie is a former faculty member here at the university, and he is a sponsor for a previous project with Tito, which was a mechanically driven prosthetic. Our faculty advisor for this project is Dr. Ramesh Vadhamurthy, and he is a professor of mechanical and mechatronics engineering here at the university. So we're going to give you guys a little bit of background on the project. Our client is a boy named Tito. He's 15 years old, and he has lost all of his fingers due to amputations from severe burns. Tito just wants to be an equally able boy, and we are hoping to design we're hoping to design prosthesis for him that will be user-friendly and that'll allow him basic daily functions. So we've got our device we built is going to be an electromechanical hand, and it's going to have haptic feedback. It should be user-friendly. It's going to be motor-driven, and we'll use myoelectric muscle sensors to be activated. Okay. So for our customer requirements, we met with Charlie Roberts a few times actually, and we basically ended up with some of the stuff that's up on the board. So we ended up with individual finger movement. We wanted to do an opposable thumb. We wanted haptic feedback for Tito to be able to sense objects. We also wanted a general payload, which we eventually interpreted as 5 pounds of overall load. And we've got some engineering specifications to go along with that. So as the project manager for this group, I have developed a Gantt chart to track our progress. We've been very busy this semester, and as you can see, we've split it up into 3 main components, which can be found as mechanical design, we've got haptic feedback, and EMG design with data processing. So for some of the mechanical stuff, we've been working on motion requirements of the hand, how it's going to move. We're currently doing loading to figure out how much stress and how much the motors will need. We're doing load interpretation for haptics, how to figure out when it's picking up when it's picking up a load, how it's going to interpret it. And for EMG design, we're currently looking at muscle movement intensively because we are going to be using EMG sensors for that. And so also the firmware development is something that we're intensively looking at right now. And for this semester, we've estimated that we will be working a total of 962 hours estimated, which we have put a big dent in already. I'm going to pass it off to Doug.
All right, thanks, Will. So Will just mentioned a moment ago that this began as a project for the Mech 340 class. You can see the example here. We looked at the features and functionality of that design and immediately began looking at ways that we could improve upon it. After meeting with Charlie for the first time, we looked at the customer requirements and we put together a list of features and functions that we wanted to improve. After that, we began sketching, and as you can see here, we came up with several different functions that we wanted our prosthesis to complete. All of these which are listed as customer requirements and include things such as holding a pencil, grasping a sheet of paper, turning a door handle, picking up a ball, and holding a cup of water. With these functions in mind, we then began compiling a list of system capabilities that would be required to accomplish our goal. We decided that the system would need to monitor itself. So, as Will mentioned also, it's going to include electromyographic sensing. This here is an example of data that we took from testing on Brett. It will also include haptic feedback and power monitoring. From there, we began sketching ideas for the overall design. These are some of the first sketches that we did, just showing the basic layout for possible sensor and component placement. This sketch here is showing the gauntlet design and how it's going to wrap and fasten around Tito's forearm, and also the sensor placement, the embedded sensors, and breathable design here for increased airflow. Over here on this side, we have a possible design for the palm, as well as actuation methods. Overall, we generated 3 different design concepts. The major difference in these 3 being the way in which the fingers are actuated. The first design utilizes a linear actuator and a 4-bar link-inspired mechanism. The second design utilizes a worm gear that would be embedded in each individual finger. And the third design would include a rack and pinion system to actuate the fingers. We performed our Q analysis on each design and compared them to the 340 design, which was our baseline, and allocated points to each of those based on the legend that you see here. And in the end, the design that used the linear actuator, it received the most points, which was nice because that's what we were leaning towards, and that kind of confirmed that we were headed in the right direction. So that was the progression of our conceptual design. Brett's up next. He's going to discuss the critical elements, risks, and performance.
Thank you, Doug. Yeah, we basically did the same thing where we broke down our product into different systems and then looked at different alternatives for each one. This is good because it also lets us do an individual risk analysis of each system. Next slide. So the big bottleneck is the human-machine interface. How is Tito actually going to use this hand? So we wanted to design our own non-contact EMG. As you see with the risk on the right and like our design factors and our tools on the left. And unfortunately, designing your own sensor is time intensive and also processor heavy. So we do have a list of alternatives. We have an off-the-shelf direct contact EMG. We've looked at doing muscle displacement with embedded pressure sensors and then also flex sensors. And then also importantly, we have the actual drive system. Looking at that 4-bar linkage, it's important to get this correct because we don't have the mechanical advantage we need. We have to use larger motors, larger batteries, and the whole thing gets out of hand quickly. So we have different actuation options, including rotary motors with custom linear actuation, tension wire, embedded worm gears in the finger, these kind of things. And then finally, we're thinking, oh, let's throw in a big LiPo battery, everything's gonna be fine. You guys have seen the videos. This is something that's gonna be moving around a lot. If it gets punctured, there's a potential he'll have a chemical burn. So we do a good job with our housing, and we're evaluating different battery options, including lithium iron phosphate. We think it's a good alternative. That being said, rather quickly, I'll pass it off to Pete.
Thanks, Brett. So what you see in front of you is our quote-unquote winning concept. It features our 4-bar modified finger linkage system driven by linear DC actuators with a sub-micro servo handling the rotation of the thumb. It'll also feature a torsion spring in that thumb to give it a little bit of play for some of the fine motor controls. Have a breathable gauntlet inspired by 3D printed air casts, and all of our desired sensory components will be packed into the hand. Our case to go forward is essentially this design is the one that most efficiently and intuitively solves all of the customer requirements. Basically, we wanted it to be intuitive enough that Tito's family could maintain it, but still complex enough that it would maintain Tito's interest in mechatronics, as we've mentioned before. The other interesting thing about this design is it's kind of plug and play, as we're calling it, and what I mean by that is if one of the features changes, the rest of the design, the body of the design doesn't have to change that much. So in conclusion, we've been hard at work, and we hope that that shows in this presentation. From here, we are currently using a solver that Brett whipped up to optimize our part sizing, as well as amplifying and filtering those EMG signals. We'll be meeting with Tito soon to see how his skin gives back the signals. As well as we're rounding third on that motor selection, and we're going to whip up some working drawings in SolidWorks, something a little bit more presentable in manufacturing. That being said, are there any questions?
Have you done any research on existing devices?
For other
Extensively.
yeah. We've looked at pretty much everything. From the 3-fingered setups to the fully automated ones to the 4 motors per digit ones. And we're trying to do it, like we said, a little bit simply and kind of elegant solution.
Like there's an actuator for the ring finger and pinky finger. Why not just make it a 3-finger with the thumb?
That's more along the aesthetics portion of things. Something that Charlie really wanted us to push is to make it look like a real hand and make it feel normal. And so we did we did it extensive, like, we're just sitting in class one day and trying to move our pinkies and ring fingers. We thought that it would still make the same effect.
Yeah.
Have you thought about giving him the option of like insertable end pieces that he could design himself?
Yeah, that would be the goal. Since this is his only working hand, if he like messes up his code or messes up his design, he'll lose a lot of that capability. So we thought about like an emergency reset button that would maybe re-upload firmware. But then eventually he is going to outgrow the brake. But yeah, we would like to keep it modular for sure.
No, I mean on the end of his fingers. So one is particularly good at pencils, one, and it comes along and says, "Oh, I need something that's," and he can make it himself. Well, you know,
Yeah.
he print his own little.
So something that we've actually been looking at is a covering for the entire thing after the fact. So that'll be something that's a little bit squishier. Kind of think of the grip that you have on a ballpoint pen, and that's something that's firm, but when put a pressure on it, it'll change shape a little bit. Something that can handle a lot of different tasks for now, but it's open to modification by Tito down the road.
We were thinking one size fits all, but that's not a bad idea.
You know, to keep his end, you said he wants to keep an interest in mechatronics. Well, let him design his own little end effectors.
Yeah.
For different things.
Totally true.
What's your biggest risk of this not being successful?
Well, yeah, the EMGs adding up quickly. I think the three we laid out are the biggest. Yeah, the EMG is something I'm very personally attached to at this point, so I've lost a little perspective on it. But then again, the linkage and then the power system. And then we do want it to be something you can program and use himself. So, but that's not a deal breaker.
Okay, thank you.